It's a pleasure to be with you all, well, this morning, this afternoon, or this evening. Let me just share my screen and we'll be on our way. All right.
Great, we can see your screen.
Excellent. Thank you for confirming. So yes, thank you so much for the introduction, and it's a pleasure for me to be among everyone today for this conference. Really, what I'm doing at the Eclipse Foundation is two things. One is take care of the 50+ open source projects we have in the IoT and Edge space. And the other one is to be out and around working with developers and architects trying to build solutions. And part of that is, of course, to be at conferences. So I'm really excited to be here among members of the RT-Thread community today. And by the way, if you want to learn more about our extensive IoT and Edge Computing toolkit at the Eclipse Foundation, I wrote this little book. So please have a look if you are interested in discovering what we have in the toolkit. And really, this is a good complement to RT-Thread-based solutions. We have over-the-air software update platforms, edge computing platforms, everything that really would complement embedded and IoT applications running on RT-Thread. Certainly, it's worth a look. And if you don't know where to start, well, it's my job to help you out. So please get in touch and we can explore together the possibilities there. All right. So for today's presentation, really, it's fairly simple. Really, three main points there. First, we'll take a step back and ask ourselves why we would need a real-time operating system. After that, we'll have a look at 4 options as RTOS go, and of course, RT-Thread is one of them. And then we'll look at various alternatives for a bare metal approach. So, do we need RTOSs? And well, this is a real-time OS conference, so I'm expecting that most, if not all of you, will answer yes. However, to understand the merits of the bare metal approach, it's worthwhile to remind ourselves why a real-time OS is useful to us as developers. And so I have a few slides covering just that. And this first slide is really nostalgic. This is the first computer I ever owned, so I'm dating myself a bit there, of course. And this is literally the most reliable computer I ever used. And the reason for that is quite simple. It was a very, very simple machine with 64 kilobytes of memory and no operating system. I mean, it was booting literally in the basic interpreter in order for me to code my programs. And I'm putting this ahead not to recommend that you build solutions today with that kind of computer, but rather to emphasize that sometimes there are merits to an approach where you strive for simplicity. Okay, this machine was reliable because it was eminently simple, especially compared to the very complex desktop computers that we use today with not only the operating system, but all of the layers of software on the top. So yeah, as a starting point, there are situations, there are use cases, there are projects where you won't need an operating system because essentially you're trying to do something very, very simple. Just gather a bit of sensor data, sending it remote to a remote location or something like that. So really, simplicity, don't forget about it. Now, operating systems in general have things that they deliver to us as developers, and really they provide tremendous value. Otherwise, no one would be using them at this point in the history of computing, right? And really, it's fascinating to see how much functional scope there is in an operating system. They provide to us APIs, things that we can call and then we don't need to implement ourselves. They provide to us hardware support, either through layers of hardware abstraction layers or directly through drivers and things like that. And of course, those are complicated things, right? Personally, I'm not an expert enough to start writing low-level code like drivers. So I'm happy that bright developers elsewhere are doing that. Of course, memory management, multitasking are important things that an operating system provides, whether it's threads, semaphores, and of course, operating system processes and things like that. Really, all the complexity, once again, behind those things are implemented for us in operating systems. From a real-time perspective, of course, one of the major benefits of using a real-time OS is the fact that it takes into account the real-time mission-critical requirements you have. And this is of course, one of the main reasons why there are so many healthy open source real-time operating systems in the market, including RT-Thread. And finally, operating systems deliver to us shared services like encryption, user interfaces, and things like that. And really, once again, the whole point is to have those things written for us, and then we exploit them as developers. So essentially, that's what you see on the right side of the slide. An operating system is there to prevent you from reinventing the wheel, especially in the case of low-level code, which is tricky to write, tricky to debug. And really, if you want to focus on your IoT or embedded solution, this is certainly one way to accelerate things. And of course, I'm once again dating myself there, but it's important to understand the difference between real-time OSs and the type of OS that we are running on our cloud servers or desktops today, or even laptops. So the fundamental distinction between a real-time operating system on one side, which is the preferred approach to embedded IoT projects, versus a time-sharing operating system. So the whole point of the OS I'm running on my laptop right now is really to maximize resource utilization. So I want to use the hardware, the CPU cycles that I have on this laptop as much as possible. And even in the cloud, it's even more important. We do virtualization, containers, and things like that in order to ensure that we really use the hardware at our disposal. And then real-time OSs are a whole different story. They are about many things, and I'm oversimplifying there, of course. But really, the whole point of this is to guarantee the latency. When I, do an API call, I want predictable latency to ensure that my mission-critical application will not kill someone, for example, in a connected car. You need to make split microsecond decisions about whether to brake or to accelerate and things like that. So you want that kind of guaranteed latency because, of course, latency is not something that's guaranteed in the case of the cloud or in the case even of my local laptop. And this brings us to another important differentiator to keep in mind in picking the right solution for your project. The difference between OT, operational technology, and IT, information technology. If you're like me, well, for a long time, I was in IT projects, writing web applications and things like that. And this is a world where, technology is off the shelf. I can buy, dozens of the same laptop on suppliers' websites. I can buy tons of servers in predictable configurations that are interchangeable. I can really literally replace one of those servers by another, maybe swapping the disks, and I'm back up. And really, IT today is about very frequent updates. And this is a side effect of the cloud in the sense that before the cloud era, we were used to maybe update our OS or Office suite every 3 years. Now with the cloud, we have updates literally every day. And that's part of the game, and that's perfectly fine because in many cases, we are not dealing with real-time mission-critical requirements. Operational technology, of course, is a completely different game. We have factories, we have water sanitation systems, we have connected cars, and really all of the systems in those particular use cases are built for a specific purpose. And of course, those are heavy capital investments. If you think about the car factory, we are literally investing hundreds of millions and sometimes more in order to bring the equipment and configure it to build a certain number of car models. And so no two car factories are alike. Everything is custom built. And all of the control systems on the factory floor really control critical infrastructure. And my robot doing a precision weld on the chassis of my new car, if it is interrupted because of bad latency management only for a few fractions of a second, then maybe the whole chassis could be ruined. And of course, there is the possibility of huge financial losses there, which means that in the end, operational technology equipment is not updated at the same cadence that you would see for information technology. You need to be very deliberate and careful about patches and upgrades and things like that, because even just an afternoon of a stoppage for a factory could potentially represent millions of euros or dollars or yens, whatever financial unit you want to use, but heavy financial losses for the organization. So how to decide which real-time OS or which bare metal framework I would be using in order to support my use case? And really, this boils down to three main points there. There are many others. Okay, once again, I'm oversimplifying since this is a short presentation, but really, you need to ask yourself what kind of hardware platform you have first. And of course, using a real-time OS with extensive hardware support like RTThread is one good way to address that particular point. Then you have to ask yourself, what are your functional and non-functional requirements? If this is just about gathering sensor data locally, sending that to a local or remote MQTT server, let's say, then, okay, maybe I can keep things simple. If I'm programming the embedded system for the ABS brakes in a car, then I have another set of requirements. And of course, there's the critical part of the peripherals and buses that you need to leverage. If you want to do AI at the edge or AI on device, for example, so maybe you need a more rich set of features and maybe even USB or PCI Express connectivity in order to integrate an AI accelerator, for example. And in some other cases, you will need run-of-the-mill, off-the-shelf hardware to do the job. So once again, considering the dimension of the connectivity provided by your real-time OS or bare metal framework is an important one. So let's have a very quick look at how various open source real-time OSs, including RTThread, are architectured and what kind of feature set they provide, just to have some contrast to see the scope of available solutions, really. And we start here with ARM Mbed. So Mbed has been around for a while. And of course, it is strictly targeted at the microcontrollers and processor cores that are coming from the ARM ecosystem. And we see, of course, there's this principle of hardware abstraction and board support packs, a bit like can be found in RTThread, of course, where partners will provide specific software packages to provide support for their particular solution. And there is in Mbed a standard driver model that really ties everything together. And then you see the real-time primitives in the RTX the subcomponent there. So you can run Mbed as a non-real-time OS, or you can run it as real-time. It's really your choice. And you see the fine segmentation in the various components. So there's a TCP/IP stack, and then protocol implementations for MQTT, CoAP, XMPP, etc. So overall, this is a fairly well-rounded package. So the one thing to remember, however, is that some of the components are, of course, provided by the core Mbed team, and some are provided by ARM's ecosystem partners. Now, is Embed a good fit for your project? Well, of course, Embed is modular, so this enables you certainly to ensure that your executable is as small as possible. So that's a good thing. Abstraction layer and great ARM hardware support are given there. It's nice to see MQTT and CoAP built in and a mature cryptography solution provided. However, Embed is about a single vendor. That's the thing. Yes, they are ecosystem partners, but ultimately it's ARM pulling the strings at the top. And there is some level of danger there. Of course, it's focused on ARM only. So if you like RISC-V, and I like RISC-V a lot, then of course Embed is not for you. And the ecosystem really for Embed is smaller compared to competing solutions. Now, of course, we cannot have a conversation about real-time OSs, or at least real-time primitives, without mentioning FreeRTOS. So FreeRTOS has been around for quite some time as well. And the thing about it is, you see this diagram is really quite simpler compared to the Embed one. And really, there's one thing to remember about FreeRTOS is that there is an extensive set of components that you can tap on. However, not all of them are directly maintained by the core team, and they have their own life cycles, which means that typically when you work with FreeRTOS, you need to figure out, okay, I will use the kernel and then maybe the built-in TCP stack, but now if I need to do a specific thing with, let's say, LoRaWAN connectivity, then I need to make sure that my hardware supplier supports FreeRTOS and provides me a library for support. But there's a kind of mix and match approach at work there, which is a bit, I wouldn't say necessarily dangerous, but will require more work from your part in the sense that, of course, it's up to you to make sure that the various versions of the components that you have worked together, that they are secure and that they work. And no one will bail you out from that, because this is an ecosystem where really it's all about, components that people piece together themselves. So you need to be careful because, of course, the core kernel and all of that is well maintained and all of that, but maybe the FreeRTOS support for the particular network board that you want to use or network chip is not necessarily as well maintained, and you could run down the road into trouble because of that. So, and of course, one recent trend in FreeRTOS is that since it's owned by AWS, they kept adding features like Device Defender, Device Shadow, which are useful, but really try to push you in the AWS ecosystem. And I'm not saying that AWS is a bad cloud or a bad ecosystem, but personally, I don't like lock-in. I like to be able to choose my suppliers and have a variety of them. So to be pushed towards a specific cloud provider is not something that I would recommend. So FreeRTOS, a very, very small footprint, mature, broad hardware support, a vast ecosystem, but once again, single vendor governance. So this is about AWS making the decisions at the top. You have this support burden. Not every component that you will use will have the same support lifecycle. Growing ties to the AWS cloud, that's not something that I like. And certainly some of the features in there, like dynamic memory allocation, are shipped as samples. And if there's one thing I don't want in my production application, it's really sample code, right? I want to be as professional and as production ready as possible. So I'm a bit hesitant when I read documentation and I see, oh, this is shipped for sample only, you will need to make it more robust yourself or something like that. I don't like that. I prefer more brilliant developers than me to do that hard work for me and then benefit from it. Third option there is Zephyr from the Linux Foundation. And here we see really a very comprehensive stack coming from the hardware support to a number of kernel services and schedulers, low-level APIs that support a wide range of buses and connectivity options, the built-in networking stack, and on the top of this, implementations for MQTT, HTTP, lightweight M2M, and CoAP. And there's even a standard application model. So there's a lot to like in there for sure. Now, Zephyr, as Embed is really modular. So when you compile, you get just the pieces that address the needs of the application. It's mature. It's got vendor-neutral governance under the Linux Foundation, which is a plus, and a growing ecosystem, although it's smaller than some of the other options. Now it's heavier than RTOS and has more limited hardware support compared to some of the other options at play in this presentation. And finally comes RT-Thread. So I don't need, I suppose, since this is an RT-Thread conference, to cover the architecture diagram in detail. What I really like about RT-Thread is, of course, the set of low-level primitives that are available, the nice segmentation of the board support packages and things like that. And of course, the richness of the stack with implementations for MQTT, lightweight NQM, and CoAP. So no need to re-implement that or even being worried about it. And from a connectivity standpoint, with support from Wi-Fi, Bluetooth, LoRa, 4G, etc., you have plenty of options to choose from. But really what's interesting in there is, of course, the extensive ecosystem of applications on the top that are not necessarily shipped with the OS, but are maintained by the community, the core RT-Thread community. And here, that's certainly a nice, very nice value add as far as I'm concerned. So is RT-Thread a good pick? Well, it's mature, certainly, since it's been developed in some form of another since 2006. It's modular as well, extensive hardware support, including very, very good support from RISC-V, and especially I'm happy to see the kind of support that's coming down the road for the open hardware groups, Core 5 open source processors and microcontrollers. That's really great. And the comprehensive collection of software packages is certainly a plus. Now, there's a bit less adoption than FreeRTOS, Embed, and Zephyr, but this changes over time. It's just, it's maybe a bit harder to find tutorials and training materials, although this is improving certainly from what it was a few years ago. And having a conference like that is literally a fantastic way to produce good content. And governance is not completely neutral. You know, I'm partial to that since that's what we do at the Eclipse Foundation. But certainly, this is not a single vendor project in any way. So at least it's better from my perspective than what Embed and FreeRTOS are at this point in time. Now, let's have a look very quickly at some contenders for bare metal frameworks. So, of course, one potential option is to use a microcontroller that can run without an OS, and a popular example of that is the Arduino family of boards. Typically, they use 8-bit or 16-bit cores with or even without a bootloader. If you need to squeeze an extra drop of storage, you can wipe out the bootloader of most of those boards, and the programs execute directly on the board. So, for example, in the case of Arduino sketches, that's a simplified version of C++. And of course, typically you will get an extensive set of libraries built by the Arduino and the community to support MQTT, REST, and things like that. So is that a good option for your project? Well, that's simple. It has a small footprint. The devices are very affordable and very power efficient. But once again, if we talk about real-time or mission-critical things, well, there's no multitasking there. There are no real-time guarantees. The code is, of course, platform-specific. So if you're trying to maximize the utilization of your code, then you will have a bit of extra work to do there to ensure that your code is cross-platform. Another interesting option is the Espressif IoT Development Framework, or IDF. In this case, this is a software stack that really targets their very popular ESP32 microcontroller. And it's a very good one, right? With dual cores and Wi-Fi, Bluetooth, and all of that. IDF itself comes with built-in support for MQTT and HTTP client, Modbus support. It can even provide you HTTP and HTTPS servers. And you can use, if you want, a special version patch for symmetrical multiprocessing of the FreeRTOS scheduler if you want to. So in the case of IDF, the advantages there are certainly the simplicity there, the multitasking support, real-time is a possibility if you use the FreeRTOS kernel, and the devices are quite affordable. But this is a single vendor ecosystem. Extensa is certainly a good architecture. It's a RISC one, but it's not ARM, not RISC-V, so of course it's a bit more limited in there. And well, the 32-bit microcontroller is nice, but not necessarily needed for all ranges of applications. And finally, our last option as a kind of bare metal framework is the Rust programming languages. And really, Rust is really attractive for constrained devices because of its memory and thread safety. It supports bare metal development, so you can use it to write bootloaders, operating systems, and applications because of the way the language is structured. And I'm not digging too much into details, but essentially, you can discard the base Rust standard library, let's say, in order to write very, very low-level code. It's got a thriving embedded ecosystem. However, there's no mature RTOS in it right now. Maybe this will change in the upcoming years. And really one thing that I like about Rust is the concept of crates. So that's the name they give to their libraries. So there's the cargo package manager, and really it handles dependency management and things like that quite well. So in Rust, variables are immutable by default and statically typed. And this means that the compiler will find most of the problems about concurrency and things like that at compile time. So you won't have buffer overflows or anything like that at runtime because the compiler is detecting them statically at compile time. It provides memory safety really without a garbage collector, which is one of the downsides, of course, of Go or Java and things like that, because you know I'm not digging in the 3 points I have in the slide. We don't have the time, but essentially the way ownership of variables is handled means that it can provide memory safety without a garbage collector. And the one interesting thing about Rust as well is that it's inspired by functional and object-oriented programming, but it's neither of those things. So it's its little own thing from a language design perspective. And so, yeah, there are, as I said, 2 possible runtimes for Rust. So when you use libstd, the standard crate, then you get Stack Overflow protection, and the main thread is invoked, for you. It started for you before the main function is invoked, and really the standard crate is, however, platform specific. So this enables you to run on Windows, Mac OS, Linux, any OS of your choice, which is supported. But then you can choose to use libcore instead. And really, this is a platform agnostic subset, but there's no heap or collections unless you add in there additional crates. And this, of course, balloons the executable size a bit. But libcore is certainly the choice to run on very constrained embedded systems. And certainly, yes, from a maturity perspective, embedded support in Rust was added after, let's say, other features in the language. So really, this is the structure, let's say, of a typical Rust application from an embedded perspective. So you need a crate to support your board. You need the hardware abstraction crate, which branches out in a microarchitecture crate and peripheral access and things like that. So you need to piece together those things in order to have a fully supported environment for your board. So once again, it's a bit reminiscent of the mix and match approach that you would find in FreeRTOS, but as I said, the community is thriving, and most of the time you will find well-maintained alternatives for all of those things that you see on the slide. So why would you pick Rust? Of course, the memory and thread safety are the #1 reason. Not having to deal with buffer overflows or things like that is really nice. It's got lots of momentum and vendor-neutral governance through the Rust Foundation and a growing ecosystem. However, you need to remember that the language itself is still a moving target. They add new features all the time and sometimes deprecate some others. And so you need to be ready to handle that. And the hardware support is more limited, especially when you compare that to RT-Thread, for example. But this is slowly improving. Anyway, so to conclude in 1 minute very briefly, just to introduce you about the IoT work we do at the Eclipse Foundation. So this is our kind of little IoT architecture that we use as a reference point in our community. And when I say we, this is coming from our committers and contributors, not from me personally. And these are the logos of the 20 to 25-ish most popular projects we have for the various functional concerns that you see. And really, the point there is not to start talking about all of those logos, but to impress on you how extensive our toolkit is and how complementary it is to what you would be doing with RT-Thread on an embedded application. So please have a look. There is probably something for you that you could be using, and all of that, of course, is open source. We are working also closely with the Open Hardware Group. We are kind of fraternal organizations in the sense that we are really joined at the hip there. And really, Open Hardware works on the processor cores and IP, the tool chains, and even the Core 5 IDE on the top of that. And in our case, of course, we have the IoT building blocks and the base Eclipse development environment that we provide to IDE developers and things like that. And all of that, we are building a comprehensive open source IoT RISC-V based stack. And it's fantastic to see that RT-Thread is one of the options that you can leverage in order to build actual solutions. So thank you so much for listening to this presentation. If you want to learn more, you can find me on LinkedIn and, of course, on Twitter, at least for the time being, as Blueberry Recorder. And we have a handful of websites here where you can have a look at things. Now, I think there are at least 1 or 2 questions in the chat. So I think we have the time to briefly answer them, I guess.
Oh, yes, yes. I was just about to ask you.
All right. So let me find the first one.
Which
Is
adoption
Espressif,
of RT-Thread?
Is
Above
Espressif
that.
IDF not supported on Espressif RISC-V chips? That's a good question. I don't know. I didn't check in detail. I know that it's certainly more mature and better supported on their ESP32, but you are correct in saying that Espressif is shipping now RISC-V based microcontrollers. So I need to dig a bit more, and I will try to find a more definitive answer, but my expectation would be that if the support is there, it's certainly less mature than ESP32 because their RISC-V based hardware solutions are more recent as well. Then,
there was a question just before that that said, which adoption of RT-Thread were you referring to as missing?
Oh, yes, of course. So from an outsider's perspective, I wouldn't pretend I'm a very active member of the RT-Thread community, well, watching from the sidelines. But it seems the ecosystem for the time being is more concentrated in Asia, and that you will find, yes, partner companies to work with, but compared to, let's say, FreeRTOS, which is supported by literally everyone, the adoption is a bit smaller there. And that's not a knock on the quality of the technology. And this is something that will change over time. As I said, a conference like this one and the presentations that will be diffused after that are slowly working to change this and, of course, grow the ecosystem. And I'm fully expecting to be back at next year's version of this event, and to continue to work with this part of the IoT open source ecosystem, because of course, the Eclipse Foundation and me personally like to work with any open source community that shares our values and priorities. So as I said, those things change. For the time being, maybe they are larger or more active open source communities from a number of participants. But given the quality of what I see in RT-Thread, I'm expecting this to change positively in the next few years for sure.
I totally agree. Do you still have your Tandy computer?
Yes, absolutely, and still in working order. The diskette drive is not that healthy. So this shows once again the virtues of simplicity, because a diskette drive is a very complicated mechanical thing.
Yesterday, I'm just going to post the link in the chat again, just in case you're interested. But yesterday I was talking about the Commodore C64.
Yes.
Which started a lot of people on their computing careers back at the beginning of the 80s.
You're so right.
And there's a company called, well, I don't know what they're called, Retro Games, but they brought out something called the C64, which is exactly the same look and feel as a Commodore 64, but it's FPGA powered. But it's site accurate. You can program it in Commodore Basic. It comes preloaded with 64 retro games, and it's got an HDMI output, so you can plug it into your modern television.
Nice.
It's almost a must-have for us old folks.
Yeah, and in my case, I never, at least when I was younger, dealt with Commodores or things like that. I was in another part of the early computing ecosystem, let's say, with the Tandy computers. But what's fascinating, I think, is IoT devices and things like the microbit and all of those very affordable boards replaced those early computers as the first step in computing for many people today.
Yeah.
And this is really, really exciting from my perspective, because you can do so much, compared to those early computers that we were using in the 80s.
Well, yeah, and the thing is, it's the ecosystem, like you were talking about the Arduino, which I use for a lot of hobby projects. It's the fact you can get little breakout boards with different sensors and just plug them straight in, and places like Adafruit have got all the little sample code that gets you up and running quickly.
Yeah, indeed. And I literally recommended a kit, shipping with the board and sensors ready to play and all of that to a colleague maybe two Christmases ago. They were looking for something to introduce a 10-year-old kid to computing. He was fascinated by robots and things like that. And it was so easy to find quality kits to recommend to get that kid initiated to computing and robotics. And to me, it's really an exciting time to be in technology, because there are so many affordable things that you can buy and use to learn.
Well, also, one of the things that you said, when you were talking about time sharing versus real time, and you're saying that in the old days, you might get an update once every couple of years. Even in 1990, I was working for a computer company over here in the States, and they created fairly big applications, but the application took 70 of those little 3¼ inch floppy disks. So an update was a huge box of floppy disks, and you put the first disk in and ran it, and then it said, take disk 1 out, put disk 2 in. And just breaking the application up into 70 parts was a major feat.
Indeed. And then you were stuck when diskette 24 was defective somehow.
Oh, yes. I mean, I remember when the first zip drive came, the blue disk that could hold 100 megabytes, which was essentially 100 floppy disks. and we could not believe our eyes. And now, of course, you get a little memory stick, a USB memory stick with gigabytes of data. Jose's just said RT Thread seems to be quite robust and have a lot of components, but isn't that a double-edged sword?
Well, you could say that maybe if you are fearful from complexity, but this is where I think the modular nature of the OS makes it really worthwhile, in the sense that when an OS is properly modularized, and I think that RT-Thread is one of those, then at compile time, if there are modules you don't use, then you don't get them in your executable at all, right? Which means that ultimately, yes, there is certainly additional complexity when you have several layers and lots of components. So of course, it's tougher to understand the whole stack in depth, right? But the great thing is that if you don't need some parts of the stack, you don't need to care about them. They are completely excluded by the build system, and so ultimately it's maybe a problem for the development team, in the sense that, of course, the larger your code base is, the more difficult it is to push out new releases and things like that. But once again, when things are modular enough, you can have those various pieces evolve on their own life cycle and piece them together in releases. So I think, at least from what I see in my limited experimentation, that this is not necessarily something that concerns me personally in something like RT-Thread, for example.
Right. Well, thank you so much. That was a fascinating talk. It's certainly given me a lot to think about. I've not really looked at Rust, and so I think that's another thing to add to my list of things to look at.
Indeed, and it's well worth the time. Personally, I like the language a lot. Would I use that in every project? Of course not. The whole point of the talk was really, here is, a set of alternatives, and pick the right solution for your project and your skill level and all of that. Ultimately, it all boils down to that. Having a flexible toolkit and is, I think, the key in order to deliver quality solutions.
Right. Well, again, thank you so much. That was a wonderful talk.
It's been a pleasure. Thank you.
Look forward to seeing you next year.
Yes, absolutely.